everyone, the glass transition temperature is of great importance for studying polymer properties. Therefore, today we will specifically discuss and study the glass transition temperature, Tg. When T is less than Tg, the polymer is in the glassy state. It is a plastic, and when T is greater than Tg, the polymer is in the rubbery state. It is rubber. Tg is the heat resistance temperature, or maximum service temperature, of an amorphous polymer when used as a plastic. For example, PS, polystyrene, PMMA, polymethyl methacrylate, rigid PVC, polyvinyl chloride, etc. It is the cold resistant temperature, or minimum service temperature, when used as a rubber. For example, NR, natural rubber, SBR, styrene Bourtadienne rubber, etc. As shown in the figure, when the material is in the glassy state, it is generally used as a plastic. When in the rubbery state, it is used as rubber. With this concept in mind, students, please consider the following questions. Are PE and PP plastics or rubbers? Given that PE's Tg is minus 113 degrees Celsius, the Tg of PP is 35 degrees Celsius. At room temperature, 25 degrees Celsius, their service temperatures are both above their Tg. That is, they are in the rubbery state. So are they both rubbers? The answer is no. Because the precondition for defining the three states is that the material is amorphous, non-crystalline. PE and PP are crystalline polymers. Therefore, they should not be analyzed using the deformation temperature curves for amorphous polymers. Next, let's discuss the relationship between volume and free volume during the glass transition. As shown in the figure, when the polymer cools, both the occupied volume and the free volume gradually decrease. When cooled to Tg, the free volume reaches its minimum. At this point, it enters the glassy state. In the glassy state, the free volume is frozen and remains at a constant value. At this point, only the occupied volume of the polymer molecules decreases as the temperature drops. So Tg is the temperature at which the free volume reaches a certain critical value. The polymer in the glassy state is a state of constant free volume. Finally, let's analyze the factors that affect the glass transition temperature. First is the effect of polymer chain flexibility. Any factor that affects the flexibility of the polymer main chain will affect the glass transition temperature. The greater the flexibility, the lower the glass transition temperature. The higher the rigidity, that is, the poorer the flexibility, the glass transition temperature is higher. For example, SiO bonds are more flexible than CO bonds, which are more flexible than CC bonds, as shown in the figure. SiO bonds are the most flexible. Therefore, silicone rubber has the lowest Tg. Carbon-carbon bonds are the least flexible. Therefore, polyethylene has the highest Tg. When the main chain contains isolated double bonds, the Tg is lower. For example, cis-polybutadiene rubber contains isolated double bonds in its structure. Compared to natural rubber, which lacks isolated double bonds, the Tg of styrene Bourtadienne rubber, which contains them, is lower. Effect of molecular weight. Effect of molecular weight on the glass transition temperature. As shown in the figure, you can refer to the empirical mathematical formula for analysis. Tg is the glass transition temperature. Tg is the glass transition temperature at infinite molecular weight. In fact, it represents the upper limit of the glass transition temperature related to molecular weight. K is a constant. M is the average molecular weight of the polymer. Both the equation and the figure indicate the glass transition temperature increases as the polymer's average molecular weight increases. When the polymer average molecular weight increases to a certain value, the glass transition temperature does not change much and approaches a fixed value. Influence of intermolecular forces. The stronger the intermolecular forces, the higher the glass transition temperature. Polymers that can form intermolecular hydrogen bonds, such as polyamides, polyvinyl alcohol, polyacrylic acid, and polyacrylonitrile, have relatively high glass transition temperatures. Influence of copolymerization. The glass transition temperature of a polymer can be adjusted by copolymerization. The glass transition temperature of a copolymer always lies between the glass transition temperatures of the homopolymers of its constituent monomers. The glass transition temperature of a binary random copolymer can usually be expressed by equations. Tg equals VATGA plus VBTGB 1 over Tg equals WA over TGA plus WB over TGB. In these equations, Tg is the glass transition temperature of the copolymer. Tga is the glass transition temperature of the homopolymer of monomer A. Tgb is the glass transition temperature of the homopolymer of monomer B. Va and Vb are the volume fractions of monomers A and B in the copolymer. Wa and Wb are the mass fractions of monomers A and B in the copolymer. Graft copolymers, block copolymers, and blends of two homopolymers. They generally have two or more glass transition temperatures. Effect of crosslinking. When the degree of crosslinking is low, the glass transition temperature does not change much. When the degree of crosslinking increases, the glass transition temperature increases accordingly. Effect of plasticizers. To facilitate molding and processing, or to improve certain physical and mechanical properties of the polymer, certain low molecular weight substances are often added to the polymer. This is done to lower the polymer's glass transition temperature and increase its flow. This is called plasticization. Most of the low molecular weight substances commonly added have high boiling points. Low molecular weight liquids that are miscible with polymers are called plasticizers. For example, pure polyvinyl chloride has a Tg of 87 degrees Celsius, making it a hard plastic at room temperature. However, after adding 45% dibutyl phthalate (DBP), its Tg can drop to -30 degrees Celsius, placing it in the rubbery state at room temperature. The effect of plasticizer addition generally falls into two categories. When a polar plasticizer is added to a polar polymer, the decrease in glass transition temperature is proportional to the amount, in moles, of the plasticizer. When a nonpolar plasticizer is added to a nonpolar polymer, the decrease in glass transition temperature is proportional to the volume fraction of the plasticizer. Effects of external conditions. First, the effect of external force magnitude. The greater the external force applied, the more the glass transition temperature decreases. That is, applying an external force facilitates the motion of chain segments. In addition, the duration of the applied force and the heating rate both affect the glass transition temperature. The main basis for determining the glass transition temperature is that, when a polymer undergoes the glass transition, the polymer's physical parameters, such as density, specific volume, coefficient of thermal expansion, specific heat, and refractive index, undergo changes. Therefore, through corresponding experiments, tests can be performed on polymer samples. This allows the glass transition temperature to be measured. Common methods include thermodynamic analysis methods, dilatometry, electrical property testing, differential thermal analysis, DTA, and dynamic mechanical analysis, DMA. Students, this lesson mainly covered the significance of the glass transition temperature, factors that affect the glass transition temperature, and methods for measuring the glass transition temperature. I hope you all can understand. Any factor that increases the mobility of chain segments will lower Tg. Any factor that decreases the mobility of chain segments will raise Tg. That concludes this lesson. See you all next class.